Hey everybody, welcome back to the second week of the Sahmati Account Aggregator Hackathon. Thank you for tuning in again. Really excited to have you guys back and for today's masterclasses. So I'm sure there'll be some housekeeping announcements and stuff that we'll do in between our masterclass sessions, but for now, let's jump straight into it. I'm really excited and really grateful that we have Sasi here with us. So I'd like to introduce our first speaker, Sasi Kumar Ganesan. Sasi was actually, he's the vice president of platform for August Networks. August is a company that's running the certification ecosystem for the account aggregator framework. Prior to that, he was the security architect of Aadhaar and a co-author of eSign. He's also the author of that Forward Secrecy GitHub project that's part of the Hack Bible resources. So when we say masterclass, here's what we mean. So Sasi, thank you so much for being here with us today, and over to you. And guys, some applause, please, for our speaker. Virtual applause. All these emojis are for you, Sasi. So thank you, Sasi, and I'm handing it over to you.
Sure. Thanks, Ariman. Okay, guys. So today's session is about our cryptography interoperability that we have built in. And obviously, most of you have already used the GitHub version that we have put at open source, the code that I have contributed for the account aggregator ecosystem. So what I'll do is I have a very small presentation. I'll walk you through the presentation, and I'll also speak about some best practices on the certification and what all covers in the certification, and also some privacy and design aspects of the solution. Okay, so I'm going ahead to share the screen. Okay, guys. We'll speak about the account aggregators, security design, privacy, and what we cover as a part of the certification as well. And account aggregator security is something little unique in its nature. That the design for it has started from the day one when we put across the paper for account aggregation. So if you would see quite a lot of cryptography being used in the part of security. I'll also explain why we chose a certain form of cryptography versus the other forms, and also some of the pitfalls that usually we come across in the cryptographic designs, and how in this case we kind of leapfrog into the best design that we could put across for the country altogether. There is a security by design inside account aggregator system. There is also a security by default in place. There is also a specific trust factors that are built in every player that you indulge in this entire ecosystem, whether it's an FIP who's involved and an FIU. So every person is a trusted party in nature, and we kind of trust them using certain mechanisms which are built in. Some of you would have used it within your current work that you've been in. This may be a redo of those things, but I'm explaining the overall view of how these things came into existence to begin with, and how we actually got in.
Okay, guys, so looks like we might have a technical issue with Sasi there. So not sure if I'm still online or not. If you can hear me, spam some emojis, please. Okay, super. So I'm going to take a short break, and we'll locate Sasi and then get back. Hang tight.
Hey guys, the drop in connection. So the security by design, as you have seen in a lot of these protocols, you would do it. Our expectation is everybody within the ecosystem understands why and how these protocols are designed, and why we choose a certain cryptography versus other layers.
Sorry, just to interrupt quickly, Sasi. Could you reshare your screen, please? I don't think it's visible.
Oh, okay. It did say it is shared. Let me try to reshare it. Can you see it?
The audience is saying yes, but I can just see a black window. So I'm not.
Okay.
Okay, so people in the audience say they can see it. So I mean that's the important thing. So
Okay.
we'll carry on then.
Okay. Sure. Sure. Okay, that's what the design is a very important factor, and I would highly recommend that you guys also do the same thing within your application, and also push every of your partners to actually follow certain design by security, and a lot of best practices are defined out here. You could use that by default. What I mean by default is basically quite a lot of us are used to configurations within our systems. We tend to use quite a lot of configurations. All we recommend is by default ensure your configuration is with the best form of security that is available. Don't go with the lowest amount of security and then increase it with configuration. Rather do it reverse, and trust every single component that you interact with. Please ensure there is some kind of a trust that you can establish. There is some kind of a token or a certificate that gets shared across this system, so that you could actually kind of trust that particular system which is involved. Now I'll quickly jump into the cryptography that is used in the account aggregator ecosystem. I'm predominantly assuming quite a lot of you are familiar at least with the first basic cryptography in place. So with that assumption, I'm quickly jumping into the account aggregator ecosystem. We are predominantly a PKI-based structure based on a public key cryptography or a public key infrastructure to begin with, we tend to use quite a lot of things from the PKI, but there are a little bit changes here and there to actually support the latest technologies and latest support of cryptography into this layer to help us a lot, because it's not just confidentiality. We are also looking at certain level of anonymity in certain cases, so that the communication between two parties can also happen a little more anonymous, and legal aspects also comes into a lot play, because we want to ensure every data that is being shared is also legally validatable and trustable in nature. Okay, and every key exchange as a standard, as an open standard, we have tried to make all our key exchange at the public key level. Okay, to be at an X509 encoded spec, and you're free to look at the GitHub code that is out there, wherein we would have defined every public key to be moved into an X509 spec, and then we would be transmitting over the line. So when we say public key, you should always assume within this ecosystem, it's going to be X509 encoded spec. So remember, it's not an X509 certificate. There's quite difference between a certificate and an encoded spec. The encoding is defined as how you actually keep the keys, and what's the format in which you keep the keys. While a certificate really means it can identify either an individual or a domain or something. So it kind of goes the next layer to actually identify, while the encoding just says the format in which you put through the keys. Okay, and there's quite a lot of ECC that we use here compared to the other ecosystems. One of the reason is we want to be obviously faster, take advantage of the smaller set of keys that are available, I'm not sure how many of you know about the ECC and their respective issues. Quite a lot of ECC curves are not really safe in nature. When I say safe in nature, we expect that that's potentially over kind of tampered with a certain government or a state sponsored mechanism. So we have tried our best not to use any such mechanism within our solution. We choose a curve called 25019. It's a very unique curve. We will look at the properties in few slides from now. It's a very interesting curve with an interesting property. Kind of helps a lot in the anonymous way of communication, as well as helps a lot in terms of bringing in the stability and the security that we potentially need for an ECC kind of a nature. Okay, and we also follow a specific technique when we do a key exchange between the entities. We call that as forward secrecy. While it's a very common aspect for the last 5 to 8 years, forward secrecy has been moved up front in its layer. Predominantly today, almost all browsers use that as the first form of communication. We will also see some more details about forward secrecy. And I think obviously most of you would have known about Diffie-Hellman, but I'll also give a layman's view of Diffie-Hellman to give an idea of how Diffie-Hellman actually works. But Diffie-Hellman is as old as RSA is. It's extremely old algorithm in reality. It's one of the best known mechanism to actually share keys between two entities, and we have pretty much used DHE in a lot of our key exchange mechanism. So it's a little complex cryptography. And obviously, you're more than welcome to look at the code that's in the open source, but I'll keep explaining why certain aspects do the way it does. So after all of this key exchange, we still don't trust that we could simply use the keys as it is. So what we have gone ahead and done is we kind of took that to a next stage, that after a key is really derived, we again derive it using a HKDF, which is an extremely complex hashing algorithm over which you can derive keys with the nuns and the keys that are being exchanged. So that the key is very, very unique to the session that is being established. So we want to be very, very specific key derivation to the session that we are creating. And the entire ecosystem, all the communications, we are expecting it to be JWT signed. People who have started using sandboxes and APIs would have already noticed that. JWT is a well-known standard, and I think it doesn't deserve a big explanation. It's a very simple JSON base64 format with a header, payload, and signature. Extremely simple enough that can be taken care. Now, I'm jumping on quickly into some basics of cryptography so that you understand why such an importance is given out to the algorithms that we selected and we do so. So if you see here, I'm listing down 3 images. In no way I'm telling that any of these images are secure. Okay, I'm just giving you a sample of cryptographic algorithms properties within the system. So quite a lot of time we don't understand the properties behind a cryptographic algorithm, where and how we could potentially use it. And this is a classic case. A wrong usage could potentially result in any of this nature. So if you see here, we have an original image, we have an encrypted image with a certain encryption and encoding modes, which could result in not really making a random image, but rather could reveal patterns of encryption. So while it's not absolute, but you could still see the patterns which are visible. So it is essential that we choose the right cryptography in nature. And the third image is a random information, but random in the frame of visual randomness. But is it really random is still a very different question altogether. Which is also something that you could look at, but I'm giving it a visual representation so that you're aware of why such an importance to a specific cryptographic algorithm is being enforced in this particular ecosystem. Okay, I'll quickly jump on to the DHE. And how DHE works. I'm not getting into the math model behind the scene. We could get in, but I thought it will be a lot more easier to give a pictorial view of a lot of these cryptographies, because a lot of times we don't tend to see the, we don't get to visualize when it is a math formula within our respective minds. So DHE is think of DHE this way. In a communication between two people, if the channel over which you are communicating is not a very secure channel. Now, how do we make sure both these entities, both these people kind of derive the same keys, right? DHE provides a very unique mathematical property over which you can derive the same key by speaking certain code words between each other. And the code words are okay to be completely publicly known. But when you derive the end result, nobody knows, and magically both of you would derive the same number back. Okay, that's the whole idea. And if you look at it, I'm representing that using a paint model. So you kind of combine two, three paints to get to a specific color. Okay, and if you see here, there's a common paint that both of you go through. So you can consider that to be your public key. And each of you have your private keys. okay, which you would see here in this second. So you combine your public and private key pairs, you get a specific color within yourself, okay, which is a specific key that you can transport. Now, this specific key gets transported, and if you look at this in this transport, nobody knows how you derived this. None of these two is revealed. The first two is not revealed, while the third one, which is a derived value, is what is revealed. And similar way here, the derived value is revealed. And now you again mix it with the secret. You get a color code, which is equivalent to this same secret and the color code. If you look at it, you will realize that we know the RGB values is what is combined to get the results, right, in a color kind of a mechanism. And mixing the right color codes would always come back in irrespective of the order of the mix, right? Irrespective of how you mix the order, the end result remains the same. So similar way, in this particular cryptographic scenario with the DHE, we are looking at a math formula. Irrespective of order in which you did the formula, the end result becomes a unique secret key that you could potentially use. So both of you, in your memory, in your respective server's memory, you created a key which looks exactly similar in both the places, and it looks almost equivalent to magical. And if you look at it, somebody who's in between this entire scenario, looking at the information that is being shared across both of these entities, only gets this particular orange and this particular blue, and with these two colors he can never derive the secret key. Okay, so that's in the color scenario, and it's exactly similar in our scenario with the DHE as well. And this is the exact reason why we tend to use DHE, because we don't want the entities to keep keys permanently in its persistent storage and use that to encrypt. And the reason for it is potentially forward secrecy, which I would explain from few more slides from now. Okay. Now, I spoke about forward secrecy and how forward secrecy is going to help us. So forward secrecy is a very, very unique property on a key agreement. Okay, when I say key agreement, it's between two entities. When they want to speak to each other, it doesn't matter who's in between them. Okay, for example, if an FIP and an FIU has to speak in our terms, and there's an AA who's in between, we don't care whether the data goes through him or it completely goes directly to the FIU, irrespective of the hop points, whether it is one hop point, multiple hop points. The persons who are in between literally can just keep forwarding your data back and forth, but they have no clue what is this information about and what is it really about. Okay, that's the whole criteria over which our communications were. And the forward secrecy is a very unique key agreement protocol, wherein a session key that is shared today, right now. Okay, so let's take a classic example. If two parties are communicating with the PKI kind of an infrastructure, you create a secret key, encrypt it with the public key, send it to the party A, which is similar to a PGP kind of a mechanism, and the party B again encrypts the actual data with the secret key and then sends it across. Now, if you see in between this, there was once in the communication, the secret key traveled across from a point A to point B in an encrypted mode. It did transfer across into the other system. Now, if an adversary is looking at this communication, when I say adversary, it's like an attacker who's looking at this communication, and today he doesn't have access to the private key, so he doesn't know about it. But let's assume that he's going to capture this entire packet on the internet and keeps it somewhere stored. 2 years later, the server A is hacked, and the private key within the server A is leaked. Now, what happens to the data that we previously stored? In a PGP kind of a scenario, what happens is now the packet that he has stored 2 years before, a transaction that happened 2 years before, now can be decrypted, which is extremely dangerous when you look at a financial kind of a transaction and privacy related work. It is an extremely dangerous part. So forward secrecy is a very unique property in a cryptographic key agreement, wherein even when such a case occurs in the future, wherein in the future there is a compromise of the private key, you still can't derive the session key that was used, because the previous algorithm that I spoke about, which is the Diffie-Hellman algorithm that I spoke about, has created its own unique key above our channel. Okay, irrespective of the channel, it created its own unique key in memory, communicated for that particular session, and then deleted it completely out of its memory. So an adversary who today collects this information, even at later point in time, cannot go to those servers and retrieve back. So remember that. So it has to be in memory and completely removed out in memory itself, that key is not available. So remember, it's not that forward secrecy protects your data, but it protects the actual shared key between these two entities, so that a compromise somewhere in the future will not result in the data that is in the past or the transaction in the past being compromised. So you could have a very, very safe transaction with the assumption that nobody could break it until even after the key is revealed at a later point in time. Okay, and this is the uniqueness about forward secrecy, and this is how we expect the entire ecosystem to also communicate within its HTTPS layer or TLS layers and other things. Okay. Now, I think quite a lot of you would have had a trouble implementing this curve, and apologies for the trouble, but it is an essential evil in the entire thing. We have open sourced this entire work for the community to help to make sure the community can actually forget the actual implementation and can actually adopt it extremely faster. As of now, the implementation is in Java. Sooner or later, maybe we'll come up with other languages as well. But it's also a microservice, so that way you could absolutely use it without worrying about the language and other parts. It's a completely Dockerized solution that's available. Now, coming back to the curve itself, ECC is an extremely fast cryptographic algorithm, but across the globe, there's quite a lot of researchers who have been pointing out that a lot of the ECC curve that is accepted today as a standard has a unique properties that are hard-coded into the algorithm and must be hard-coded into the algorithm. It's not that the algorithm itself is unsafe, but some of the properties that is accepted as the only certification values, okay, are hard-coded into these algorithms. And the expectation is there are certain countries who could have compromised those values. And that is the reason why they have hard-coded these values, because there is no scientific reason behind hard coding those properties in place. So quite a lot of curves have this problem, and I hope everybody knows what a curve is. A curve is curve and an elliptical. Don't think elliptical means ellipse, or it's not like an ellipse. It's like a if you could draw any kind of line in any way you want on a graph. The XY points becomes the curve, and any point in the curve can be represented by an X and Y axis. Okay, so your curve is not just always like this. It go like this. It can twist. It can turn. It can be completely any way it needs to be. And each of these curves, the algorithms behind them, the quadratic equations behind them are extremely different in nature. And there are quite a lot of curves that are defined. This particular curve that we have selected, which is 251,119, has some very unique and interesting properties, which suits the environment that we are working towards. Okay, one, it kind of avoids implementation related pitfalls. So why is implementation related pitfalls are very essential? Because in the past we have seen that when implementations are not accurate, okay, for
Okay, so yeah, I guess you guys know what's going to happen. We're going to take a break and try and get Sasi back and be back in a second.
Sorry guys, I think I lost you as well. So if you search in the Google for Infineon RSA prime number, you would see tons of research papers which are explaining how a certain form of implementation of generating a RSA key. Okay, it's not that RSA algorithm itself is weaker or any of that sense, but the way in which you generate a key kind of resulted in the keys being predictable in nature. Obviously, it takes a lot of science to predict it, but absolutely predictable. Okay, which is a dangerous build such big solutions across the country's scale. So it was very important that we choose something which avoids any implementation pitfalls, and you would see the curve 25119, irrespective of the libraries we choose to use. The pitfalls are extremely limited in that sense, that you could assume that a person who has implemented this curve most probably at 99% is going to give you better result than the other forms, wherein you're very implementation specific. So that's a big advantage for us, and as an open ecosystem, it's something welcoming for us to use that. Next is this particular curve is also immune to quite a lot of timing attacks. Timing attacks in cryptography is basically you generate a key, and there's a time that it takes to generate a key, and based on the time it took to generate multiple set of keys, we could start deriving what could be the number that the system could have used in order to create it. So this algorithm this curve, one is it is uniquely faster, and second, it is really benefits from the fact that there's not much timing difference that you could ever find to launch a timing related attack. So it's kind of has this unique property. And the best of all with this curve is the fact that the public key of this curve could be a completely any random 32-byte string. So that way you can't take a public key and think that is this part of the curve. Any 32-byte string could be a part of this curve. So that is a very unique property of this curve, and that kind of gives us a very added advantage and an edge towards what we want to try and achieve in the anonymous layers and the cryptography layers. Okay, that is why it is curve 25119. And the other factor is there is also quite a lot of curves in ECC. Unlike RSA, ECC has a cryptography specific curves, signature specific curves and implementations. In this case, we have a single curve which can satisfy both of it, because it's birational in reality, which is very similar to the word isomorphic in sense that you could twist it and then create a signature around it, and you could validate it. So ED25119 is a signature concept. Okay. So now you understand why we choose forward secrecy. Why is it ECC with a specific key and specific ECC there? Okay. Otherwise, the better known algorithms are definitely RSA, but we choose ECC here to adapt to the lower end of the phones and easy to create keys, faster to make a transaction happen. And if you look at it, one of the basic assumption in the key exchange is we are going to assume the network layer that over which you're going to communicate could potentially be dirty. Means it could be compromised, or there are hop points between them. When I say dirty, it just literally means you don't have a direct, clear, established channel between two entities to communicate. Rather, there may be hop points between, or you're communicating over internet and you don't know who's watching out on you. Okay, it assumes those two layers, and with that assumption, every single request that originates, okay, as a first action flow within our system, we expect it to have a new ECC key pair. So don't try to remember ECC key pairs in your memory, in your service memory and other parts. Create it, forget it. Okay, that's potentially what we're looking at. Create it, use it, forget it. It's all for per session. It doesn't cost you anything. It's extremely lightweight in nature. So you're more than welcome to actually not to store it in memory and all those things and struggle to cache these keys. Rather create them. It will be faster for you and it will work very efficiently. And in terms of security, it yields you for better results. Okay, and you create this key pair. You exchange this public key. We spoke about DHE. Okay, a DHE exchange happens, and the public key is exchanged between two entities to derive the secret key. Okay, similar to the picture that I showed you in the paint, right? You have a common paint, and then you have this secret that you created. You mix them both, you get a unique key, then you exchange them. Similar way here, you get a public key, you exchange them, you mix them with the private key this side, private key with this side, you get a very unique property, and from there you start deriving the keys. Okay, so you get the derives, and how do you know that you're speaking to the right entity, right? If you see, most often there are two mechanisms through which you can ensure you're speaking to the right entity. One is a certificate that is available for you, so that when you go to www.google.com or sahamati.org.in. Just by looking at the certificate that shows up in the URL, you know that it belongs to Sahamati and issued by a trusted certificate authority. So that way you could potentially use that information. But in case of our solution, we have a centralized token issuance mechanism, which is in Sahamati. There is a centralized token issuing mechanism. So every system that interacts with our ecosystem gets a token and an identity token for themselves. And they exchange this identity token to prove that, hey, I am who I am, or I am who I claim to be. And just by validating this token, you know that this is a trusted entity. And then you can allow the entire exchange of communication and the protocol to happen. Okay, so that's a one way to make a trust within our systems, and you use DHE to derive the keys. And once we derive these keys, it is not that we take this secret key that is finally derived and use it as it is. We also add some more extra properties into it to bring in that randomness, bring in that uniqueness that to particular session that we want to create, right? So we use something called as nonce within the exchange when we do the key exchange, along with the public key. There are also nonce that are exchanged. So we kind of combine this newly generated secret key from the DHE and the nonce together and create a very unique session key. And that session key is potentially now used to encrypt the data and make the entire transaction. Okay, and use that session key only for that transaction and forget it. That's potentially how we expect it to be there. Okay, so this ensures that nobody could see this data, even if it goes through multiple hop points. The person at the hop point, even if he stores this information, he cannot decrypt it at a later point in time. A compromise of those stored information at a later point cannot result in people's data being shown up online. So you would have seen several times there is passwords that are being compromised from some of our most trusted sites, and these passwords gets derived in open. But in this case, our data cannot be opened up in this way, provided you ensure that every session has this unique set of keys in there. And we also did another uniqueness that the ECC, if you remember, I told it is a public key and it's not a certificate. And this way, it doesn't identify a particular entity. So when two entities are speaking to each other, they through a hop point, which is our account aggregator, FIP and FIU speaks, they do not know to whom they are speaking to, and kind of results in that level of anonymity that it doesn't know whom the user is working with, and gives that freedom for the user to choose the person to whom with whom in the ecosystem that he would work with to make the entire transaction work. Okay, so that full trust and anonymization is built into this cryptography layer as a part of the design. That's why we said it's secure by design, and we kind of put the trust layer right into the design itself, rather than expecting that the trust could be something that could be configured by somebody else at the later point in time within our ecosystem. We use a data-centric security. When I say data-centric security, everywhere the data moves, we expect it to be secured. We have taken care in our design, and we expect the same level of security to be taken care when you're storing this information, when you're transferring this information, when you're going to show this information to the end user over a UI, when you collect the information from the user, whether it's a scanned copy of this information that you're collecting, or the user is going to type into your ecosystem. We expect that all these things is potentially in a certain form of encryption as defined in our design. And as much as possible, please adapt to the same designs so that you could reuse. One is you could absolutely reuse the code that is available for you at literally no cost. And second, you don't need to worry about larger thinking about whether the cryptography that you chose is the right one or not. And I have given you what we consider as personally identifiable information and what you want to protect in there. Okay. So hopefully this kind of helps you with the aspects. We'll quickly look at the privacy side of the story. There are multiple ways in which privacy by design is well introduced into our system. In some places, we have left it for people to look at it. I mean, to the implementer's choice. But recommendation is be in line with the design, be in line with the design thinking that is put in place, so that every one of us do the right thing. And remember, it's a complete ecosystem. One person being hacked kind of ends up with a situation where the entire ecosystem, the trust in the entire ecosystem is actually brought down. Right, and it's extremely important that we avoid such a situation within this ecosystem, and that is why we emphasize quite a lot of things on the design, and that is why the certification and other things are also pushed in hard. While you may wonder, while there is quite a lot of designs that we have put in place, why does the certification come in? Because one person doing a faulty implementation could result in entire ecosystem being questioned, and entire ecosystem data being lost, and we can't afford to do it at this point in time. To have a situation like this, we need to leapfrog out of that situation, because you have quite a lot of population in this country who don't understand digital technologies, and the trust of them is built by by us proving that this is a very reliable, robust mechanism over which they can do. They can emphasize transaction on. Okay, and this also eliminates quite a lot of risk and insurance costs for every one of you, that there's a very less chance of security incidents. Then kind of it makes your life better for everybody. Okay, so by design we isolate caller's identity. We expect you to mask the end user's identity in quite a lot of places, which is well defined in the document. I have also defined certain concepts of anonymization and some things that you can look for in anonymization as well. If you belong to a data side of the ecosystem, I'll walk you through that as well, which could be interesting. And we also speak quite a lot of places in with tokenization. Remember, a hash of a data is never a token. Please don't do that. I could see quite a lot of people tend to take data and then tokenize it. We don't consider that as a token. We consider that equivalent to the data or derived out of data, which is the wrong thing. When we say tokenization, we absolutely mean it's a random with no relevance to the actual data. So, for example, let's assume you have a random number generated. You kind of have the actual data, you give the actual data, fetch this random number, associate this in a separate database. This random number has no other meaning except that in this database, it kind of isolates, it points to that record. Now this is a token, but you give an actual data, hash this actual data and derive some token, we don't consider that as a token. It is still a derived data, and a leak of data could potentially result in a problem. Okay, and the classic example for those stuffs are your passwords kind of situation. Even though you hash your passwords, it gets leaked out because of some of the flaws in the way it is implemented, as well as leakage in one place results in the same data being tokenized once again to derive the result, which does not yield the good result that we wanted. Okay, quite a lot of mandate on OTP in there. So if you're going to use an OTP, please be RFC 62338 compliant. Don't use a random number and say that you're an OTP compliant. While we don't mandate it, it is not advisable. You may not get certified if you're not specific RFC compliant in nature, because you have no way to prove that your OTP is really random in nature. Okay, all notifications should be sent along with the context. Remember that every OTP that we look for the context over which an OTP is sent, so that there is nobody who could call somebody and spam or do a social engineering kind of an attack. So that is a very essential part. Even though we don't mandate such things in the spec, it is part of the implementer's choice. But we would recommend highly that you do this. Otherwise, in audit, for you to get clearance would become tougher in nature. How do you associate a context for a specific OTP? So is this OTP requested for a specific need, and only for that specific need you could accept this OTP is a very important part in the entire auditing and certification. I'll quickly jump upon the certification. In here, I think quite a lot of you would have questions questions on the certification. I'll explain some of those things as much as I could. And any questions, we will take it up later. Certification looks for implementation and conformance to the API. So when I say API, it's the entire standard together. We look for, have you implemented it correctly? When I say implementation, it is not just the code that you wrote. It is about the API, the code that you wrote, the way in which you have set it up, the way in which you're storing the data, the way in which you're deleting the data, the way in which you're keeping track of an audit record, the way in which you're interacting with the third party or interacting with the actual regulated entity and fetching the data out, and the storage of the regulated entity. Altogether, certification looks for as a whole system, and don't expect that I have done my API and this looks correct and I will be certified. That's not true. It has to be a full setup. Okay, as I said, it's based on a given setup. Are you doing the right things? Are you doing the right setup? Are you doing the right stuff? Do you have the right processes and policies to follow? Are you ensuring that the given setup is at its topmost security at any point in time? Remember, one entity being broken essentially means the entire ecosystem chain is broken and the trust is broken, and data being leaked is not a good sign in any nature for us to get out of it. And getting out of such a trouble would be extremely complicated. Security scope, as I said, this entire scope would be data protection at rest and in transit. And in our design, quite a lot of transit we did take care, but we expect you to take care of the rest form of the data, and also take care of any other form factors that you are using to keep the data, and any other internal communication that you are doing. We want you to be aware that follow the similar, extremely similar mechanism to achieve this. Certification has two parts. One is the assessment itself. Another one is a full-fledged audit. Okay, assessment itself is a quarterly thing. You do it for yourself. Basically, you kind of self-certify yourself to tell that, you know what, I'm following all the best practices. I have assessed using the automated toolkit. Everything seems to be good here, and I have followed these best practices, and here is the evidence for it. It's kind of a assess ourselves kind of situation. Audit, by nature, somebody comes in and looks at this information that you're providing him and checks, did you do really what you say you did? Is what the audit potentially does. There are three kinds of it, and I've listed them here. Certification is the first time you get it, and recertification is after every 2 years you kind of get that done. And surveillance audit is a very similar audit. You don't get a certificate, but it's a way to validate that are you still doing what you said you will do 1 year before. Okay, so when you start the certification, you're going to tell these are the things I will do, and these are the things I did, and you're going to provide evidence. And 1 year later, you're going to provide evidence once again that for the last 1 year I did what I said. Is the surveillance audit. And intermittent audit is something that happens occasionally when there's a huge API specification change, not a minor changes, but when there's a big API specification changes, then we may be needed to do an intermittent audit to ensure that those specifications are adopted correctly and the practices that are need to be confirmed are confirmed during that time. Next, what do we look for in certification? It looks for conformance to API, to the central registry, your proper HTTPS channels being used. It's all completely automated in nature for those things. We also look for a full functional flow with the positive scenarios. That is also automated. We also look for access control. When I say access control, what it really means is we look for all kind of negative scenarios. Negative scenarios take somebody else's data, manipulate it to look like somebody else, and try to make the entire API to see if the API responds back with anything different. Is it doing the right thing? Is it validating the stuff that we think it should be validating in there? Because when you write a specification as a full document, sometimes you would have written that in a single line, but the design for it needs to be adherent to it. So, for example, a consent of one user can
Guys, I don't know about you, but I blame hackers. Could be North Korean, Russian, Chinese, no idea. Clearly, they don't want you to find out all the security information. So, I guess we'll take a break and we'll be back shortly.
Okay, guys, I hope you can see my slide. So I'm not sure exactly where it was lost. Was it during certification or was it in best practices? I will just quickly touch the final thing that I spoke about certification and get into the best practices, so that even if I have missed, you would get that idea. As said, the certification looks for the conformance to the API, the central registry, HTTPS. We look for positive functional flows. We also look for negative functional flows. We also look for security-related problems in your API, such as, for example, a consent API received for a user A, can we reuse it for a user B and obtain the data? Can we misuse some of these informations? Can we toggle around these values and see if the system is responding back and other stuffs? We kind of do all of such validations in a pretty automatic way to ensure that the API does the right thing. On audit, we also look for data retention, data protection. How are you protecting it? Backup and security around that, and your systems and your processes, and the procedures that you follow to maintain an implemented system. All together, we look at from the time the data originates to the time the data goes out of the particular system layer. We look for everything. Is it in line with the security guidelines that we are asking it to be? Right, that is being validated in every single setup that is being in there in place. Now, jumping on to the best practices. In no way I'm telling that this is the final best practices, but I would like to iterate the fact that these are some of the best things that you could follow to ensure your data and your systems to be trusted more than ever. Follow CIS controls. You can search for that particular keyword in Google. You'll find tons of materials around it. There's a very nicely defined Excel sheet for you to actually look at and follow. It's very simple questionnaires asking you specific information, and you could simply mark it yes or no. That would give you a clear idea of what level of security that you need to put into your systems. Okay, if possible, design your storage level encryption using keys derived from the end user. That's a very unique solution. I've used this design for almost a decade now, and it extremely works well in a privacy kind of a scenario, wherein the key that you use to encrypt a particular record of a user is in fact derived from the user attribute himself. So until the user logs in, you can't open up the data. That kind of a design solves the problem of a backend system trying to open the data without the user's knowledge. So without a user's knowledge, you can never open that system. When I say user's knowledge, user has to give a specific key or an entity for it to be opened, and only then that particular record is openable, and it cannot be opened until he gives that value. So there are tons of ways in which you can design it. You can search for zero knowledge storage. I have designed it for one more open source software. You should be able to see that design in there, and you could adapt it. If you need more information, I have my personal ID out there. You could drop me a mail and I could help you out with that. The encryption algorithm, we're looking at 256 bits or greater. We're looking at AES kind of an encryption at a symmetric level. Public key and other things, you already know what we prefer and how we have defined it there. But at a cryptography level, at a basic data level, we're looking at an AES 256, nothing less. Higher is okay, we don't mind. Storage of keys, we're expecting the keys to be at a level 3 compliant device, and I ensure that you follow all the best practices to keep the keys in a very, very safe place. Remember, as I said, compromising key in one system could put the ecosystem in trouble, and we don't want that to happen. Quite a lot of anonymization which we spoke about. There are some places we have already told about things like data masking and other stuff. So we have already explained tokenization, data masking, and partial masking and other things. In anonymization, there are two mechanisms that you can use if you're a data side of the story. If you belong to the data side of this ecosystem, one is you can generalize. Other one is you can suppress. So generalize is basically, for example, if you have a huge records of information and you want to tell People between 20 to 25 predominantly takes a loan of this value, and these people pay, they repay with repayment capability seems to be at this percentage, and all of other things. You are absolutely able to tell that. That's generalized. You can even go to a district level and tell that at a district level, this is how it is, which means that giving a loan in that district at a higher level is predominantly good. You could do all of that with a generalization kind of a scenario. Suppression is a very unique mechanism wherein if you have a full record set, and if you could take the sensitive columns in that record set and simply mark them as stars. Okay, I'm saying star just as a way of anonymous. You could mark it as just star or anything for that sense, which is no meaning, which means between record A and record B, that particular attribute remains same, and there is no way for somebody to derive it. Okay, and quite a lot of times when I work with anonymization, people look at K anonymity, but my view is K anonymity, you tend to lose a lot of sites. You tend to, at a larger scale of data like what we have today here in this kind of an ecosystem, you may end up with a problem. Look for T-closeness principles, remove outliers in your data. You simply remove it out. That would be the better way of getting the T-closeness to the expectation that you want. Okay, those are some of the guiding principles. While based on what kind of data you deal with, what are you trying to achieve, the anonymization extremely varies. So it's very difficult for me to give in one session full details about how we could actually do this entire work together. But these are very interesting property for you to anchor around and start looking at things in place. Okay, so with this, I'm kind of ending my session. I think most of you already know my mail IDs and other stuff. You also know my GitHub ID. It is G Sasi Kumar. I also have the forward secrecy code out there for you guys to use it. I have my official ID as well here. You're more than welcome to communicate to me back with any relevant things that you need. Okay, and thank you. Appreciate for all your time, guys.
Thank you very much, Sasi, for that great talk. Guys, we're really lucky to have Sasi, help us so much in this ecosystem. So thank you for your talk once again, and thank you, audience, for listening and appreciating it. We can take maybe 5-6 minutes worth of questions before we start the next presentation. So Sasi, there's some questions that come in for you. There's 3 questions. I mean, 2 questions basically. Could you see them on the right over there?
Yeah, I can see them on the right. So three questions, right? What is the flow of data? Say FIU shall execute a consent artifact, then it would connect EAA, which would in turn approach FIP. Data shall be released using a cryptographic keys, which would then reach the FIU, then encrypt the use of data. So I don't know if that is a question or you're asking me is that correct? It does look correct for a specific flow. I don't know which flow we are speaking about, but there is a flow which is in line with what you are listed there, and you're absolutely right. The cryptography is initialized between the party which is sharing the data and the party which is receiving the data, and in between the account aggregator remains with no data at all. What's the encryption used for FI data? So data at the data level, our encryption is an AES 256 bit. Majority of the work that we have done is to exchange the keys between these 2 layers and how safely we can get it there. And AES GCM is the cryptographic algorithm explicitly that we have used. So you can consider as AES 256 GCM as the key. Okay, next set, what tech stack for certification testing that will be used for the scans? So right now, the tech stack that is there in the certification, it's a Python and Node based servers, plus some of the security scanning tools together is what is used for it. So it is a Node.js plus Python. and some security tools combined is what is being used for the certification, to build the certification kit itself and the testing itself. But otherwise, it's all REST compliant. So a lot of mark servers and other things are built in to test a specific entity on the flow together. Very interesting one. I would recommend if you could take a look. You'll see that. Development, key exchange, and code details. All things will be managed at FIU and FIP side, right? As of AA, we are on terabyte. Yeah, you're right. We expect the FIPs and the FIUs to be extremely bounded by the key exchange, because the data is transferred between them. is a very consent side, and you have to still look at the consent for that nature. And definitely you need to validate the token. You need to validate your incoming data, and the signatures are absolutely right for you to actually take the data and forward it back. Right, because you are like a mediator right in between both these entities, and please look for the signatures and ensure they are valid data before you forward. That way, any miscellaneous data kind of is trapped right in your place rather than going between these entities. All participants will be using the same monotogamy variant of 255.1.25119, correct? Also, as far as I know, I believe it is susceptible to side channel attacks. Okay. Almost all cryptographic algorithms are vulnerable for cryptanalysis and side channel attacks. There is no doubt about it. We are not in no way we are telling that it will be safer, but out of what we have, these are the best out of the solution. So let's just to walk you through. Code 25009 is an algorithm which doesn't result in a timing related side channel attack. So you can't, based on a time, you can't derive things in place and try to find out anything wrong with it. But obviously, cryptanalysis is something that you could definitely find out, right? Cryptanalysis is a lot more hectic task, and no way we are telling it's not possible. Yes, it is possible. It's a complicated, but if you look at the data algorithm that we are using, we are with AES 256 CTR GCM. There is no theoretically or more than theory. There is no practical evidence that exists today on a CTR wherein you could break through the system. And if you look at our designs, places where there are some side channel attacks that are possible, you would see nuns being predominantly used as well, along with the key exchange and other things. And the reason why we use those nuns and the randomness and other stuffs is to protect against some of those side channel attacks and the data related attacks in place. Could a detailed document with the certification process and guidelines be shared and published? What would be the cost of the process? I think absolutely we could do that. I think that's a very important thing. We should ideally do that. We will definitely get that done for sure. I think Nickel, right? Okay. You are trying to make a point around security aspects of user consent, and in middle we lost your stream. Can you recollect the thoughts? Good question. Now, where do I see that? By any chance, if I know the slide numbers, I could get over with it. But anyway, I could. So consent. Consent is a very important part in this solution, right? We try to use the consent as a way to build the trust for the end residents who actually use this digital site. And we are also trying, I mean, we ourselves at a personal level are going to be users of this system. Our family members, our people whom we know are going to be users of this system. We don't want the system to take us for granted. We want to be clear when and how our particular data being used. So what we have done with the consent is a very unique framework in line with the MATI's consent framework, electronic consent framework. An account aggregator acts as a mediator in this sense, which essentially means I, as a data principal, and the account aggregator is the person who centrally manages and maintains my authorization of sharing data to whom and when and how. And this consent is a very important part to make sure that the consent is validated by against every single transaction. That is something that we test in the certification as well. Is the consent validated in every single transaction? Even though we give a consent ID as part of some of the transaction, it is expected that you would validate the consent and make sure that it is not crossing the expiry date. The dates mentioned in is absolutely true, and you are still within the limits of what the consent is provided by the end user. And until a consent is provided, no data is moved at any point in time in any form and any way. Is how we are looking at it. And if you want to be very, very close to the consent and consent related privacy designs, I was speaking about a system called a zero knowledge storage, wherein you kind of encrypt each record of a user along with a certain identity that the user is going to provide you with. And that way, as a backend administrators or backend users, nobody would know the actual data. And in order to know the actual data, they need to give you that particular key that the user has to provide. Maybe it is a login username from the user, or login username and a password by the user, or it's an PAN card number or something that the user provides as a form of entering into your system, and only then that record can be unlocked. Enhances this mechanism of the consent and the consent driven and the privacy side of the story. It's a very, very interesting way of applying cryptography on your data that could help you with the consent as well. I believe this was the thought that I had in mind. I'm assuming that that's what I was trying to convey, and probably somewhere in that connection was lost.
Awesome. Thank you. So everybody, just to remind you that in the Hack Bible, the fourth resource number 4 in the Hack Bible, is actually a detailed overview of all the security workflows in the account aggregator framework. So it covers, for example, who the FIU chooses the parameters for the curve, how those parameters are sent across, how secret key is generated, public key is exchanged, nonce is generated. All of that is covered in that document. So make sure you do read that. And then if you have further questions, Sasi was kind enough to share his email ID, which I've also put into the chat. So if you do have questions after that, then you can reach out. Obviously, please be mindful of his time and bandwidth. And Sasi, thank you very much once again for this. It's been really useful. Yeah, we hope to show you our final projects at the end of the hackathon, and hopefully they pass your security smell test.
Sure, everyone. Thank you. Thanks, guys, and all the best for all your work.
Amazing. So, guys, we'll be back in about 5 minutes with our next presentation, which is an insurance tech masterclass by Anand Datta of Nexus Venture Partners. So, if you guys have around 5-7 minutes, just hang out at the social lounge tables, and we'll see you soon. Thanks again, Sasi.